Hey everybody, Vade here. So last video we went over the proofs of the properties of logarithms. And so those actually use the properties of exponents. So now we're at the properties of exponents. So with the properties of exponents here, there isn't really a formal proof I can give for this, or somewhat formal proof. It's just kind of intuitive, right, through examples. And so that's what I'm at least going to try to do today. So we're going to look at examples and just kind of generalize from there. I know that's not ideal, but you look at a lot of YouTube videos, they're just doing the same thing. So I couldn't really find a reference. So let's first start off with the rule here. A to the n times a to the m equals a to the n plus m. Well, let's think about this, right? Remember, the base is the same, but the exponents are not necessarily the same. So let's let, a equal to 3, and we'll let n equal to 5, and m equal to 2. So we have 3 to the 5th times 3 squared. Well, if we think about this here, this will be 3 to the 5th is just 3 multiplied by itself 5 times. So 3 times 3 times 3 times 3 times 3. And then 3 squared is just 3 times 3. So now let's count the 3's here. 1, 2, 3, 4, 5, 6, 7. So this is just going to be the same as 3 to the 7th. Don't you notice that 7 is the same as this 5 plus this 2? So we can just add them. Hopefully that's kind of intuitive. All right, what about this one? A to the m over a to the, or 8, I'll just use n and then m. A to the n over a to the m equals a to the n minus m. Okay, let's use the same a, n, and m for this. So we'll have 3 to the 5th over 3 squared, right? If you think about this here, this will be 3 times 3 times 3 times 3 times 3. Right? 3 multiplied by itself 5 times, and then 3 squared, so 3 times 3. Let's cancel out, 3's, right? So now we're left with 3 times 3 times 3, which is 3 cubed. Can't we just get that by subtracting this 5 with this 2? So 5 minus 2? 3 to the 5 minus 2. All right. Hopefully this makes sense. Okay. I know examples are not ideal, but, it should hopefully be pretty intuitive. Okay. Now let's go on to a to the n, or let's use black, or I use blue here. A to the n to the m equals a to the n times m. So same a, same n, same n. So we have what? A is 3 to the 5th to the 2nd, right? 3 to the 5th to the 2nd. So 3 to the 5th squared. Okay, so if we think about this here, we have 3 to the 5th, which is 3 times 3 times 3 times 3 times 3. And then that's squared. So that'll just be 3 times 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 3, right? Because it's a squared. Right, so this same quantity would be multiplied. This same quantity right here would be multiplied by itself. That's the squared. And so now, how many 3's are there? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will just be 3 to the 10th. But wait, couldn't we just get 10 by multiplying this 5 with this 2? Right? Wouldn't this just be 3 to the 5 times 2? Right? That would be 3 to the 10th. Okay, now this one, let's say a, and by the way, It's not really explicit here. Like, I guess if we have like a b, let's have b now, a b to the n, okay, is the same as a to the n times b to the n. So I'm going to let a still equal to 3, right? A equals to 3. We'll do b equals to, I don't know, 15. And n is 4. Or n, we'll just do n. What was n before? N is 5, okay? So we have 3 times 15 to the 5th, okay? So if we actually did the computation here, so 3 times 15 is 45, 45 to the 5th. Now, I'm not actually I probably should have picked a smaller number, but if we do 45, 45 to the 5th here, we'll just get this huge number here. 184528125. I don't know if I'm off on this. Just use a calculator. Again, bad numbers. But if we actually did, like, I don't know, if we did then 3 to the 5th times 15 to the 5th, right? We just kind of distributed this here. We would also get this value. 184528125. And so kind of intuitively here, right? I could just, using PEMDAS, go straight into the parentheses and do 3 times 15 and then do that to the 5th. Or if I just distributed this here, I see that I get the same result as just doing 45 to the 5th. I could just do 3 to the 5th times 15 to the 5th. So again, I know I keep saying this, but these are not really ideal. If I find some kind of formal-ish, kind of easy to understand proof, I will update this video. I will make a new version of this video. But for now, this is really all I got. I mean, these are all kind of intuitive, It's just kind of generalizing these things. I mean, honestly, I would say you probably shouldn't even just, like, the only reason why you want it in these explicit general forms is because that when you're dealing with, like, x's and y's, it helps if you know it in this sort of explicit general form. But if you were just dealing with just constants and numbers, like 3 to the 5th squared, then, yeah, you probably didn't even need to know this. You could just work it out like this, like how I did here. Just work it out. But it's just, there's a reason why it works, and it's because if it works with numbers, it can work with variables too, for the most part. But yeah, hopefully this is kind of intuitive. I'll update this video if I find anything better in terms of explaining. But hopefully this kind of does the job, I guess.